Boom. All right. Question. Oh, I forgot to grab my book. Oh well. Do I have? No, I just have answers here. Well, see if I need to go back and get my book anyway. Any questions on chapter 30?
Are we doing the same thing like we do quiz? One quiz and then break into the other?
We can. Is that what you want?
Yeah. So I guess we can go over one chapter, do the quiz, and then go over the other chapters.
All right. Sarah with an opinion? Okay, somebody nodded in support and the other person ignored you completely. So, all right, so we'll just stick with chapter 30. Questions on chapter 30? You know what? I think I am going to need to grab a book. It'll make for some exciting video, but I'm just going to let the video run. Be right back.
Did you do all of the questions? Oh.
It's too complicated.
I didn't really understand it.
I'm not either.
It's a short explanation, but the heck they were doing.
I figured since it wasn't gonna be on the quiz, I didn't bother.
Yeah, I think that's fair enough. I would guess 20 minutes.
All right, problem 24, chapter 30. So we have the square. Wire is bent in the form of a square with a loop side L. Steady current flow I in the loop. Determine the magnitude of the magnetic field at point P in the center of the square. All right, depends on how much from scratch you want to work this, but I assume you want to work it from scratch. I know conceptually that if I have a current that's flowing counterclockwise, which I think was the indication in the drawing, yeah, that the magnetic field is going to be coming out of the board inside, into the board on the outside. So it's going to be because for each of these currents, if I have a current going to the right on the bottom, the magnetic field is coming out on top, in on the bottom, here, out on the left, in on the right, and so on. And because of symmetry, all I have to do is calculate the magnetic field from one of them and just multiply by 4. I know this length here is L. I have a point there. And presumably it is not long enough in order to use the infinite wire approximation. So we're going to be using mu sub r. So I know that the differential of the magnetic field is equal to u sub naught over 4 pi. Man, suddenly I'm blanking again. I'm pretty sure it's 4 pi, but I know that there's one of them that has 2 pi in it.
Pretty sure that's right.
It is 4 pi, okay. And then the current form, I dl cross, I'm going to do r over r cubed. There's also, I think that's the way the book does it as well. You could also do r hat over r squared. That works just as well. So in essence, I'm solving this problem right here, where this distance here is L over 2. If that's 0, this would be x is equal to negative L over 2, and that is L over 2. Hopefully some L's will cancel out. I take a differential. So like dl right there. L over 2. And this position right here is x. So let's come up with a couple other things. I know that this distance right here from my differential to the point in question is r. That r right there. My vector r is, well, if I set up an I hat, j hat coordinate like this, well, if I set up I hat, j hat like that, what's the direction of k hat?
Out of order.
And from memory or another tool? You're correct. But why do you say out of order?
It'd also be the right hand rule would also tell.
Yep. I cross j is k. So my vector r hat is, well, it's going to be x I hat plus L over 2 j hat. Let me take a moment to think through the signs here. That distance there is x. X is negative in that spot. I think I'm going to be good with signs. All right. If my sign is off, oh, it's not going to matter. It probably should be a negative x I hat, but I don't think it's really going to matter here. All right, so therefore my vector magnitude of r is the square root of r. We're sophisticated here. X squared plus 1/4 L squared to the 1/2. dl is a vector along here. So dl, and suddenly I'm making my d's differently than I've ever done before. dl is a vector in the direction of the current flow, so that is in the I hat direction given the setup, and it is also dx, so this would be I hat dx. And so now, sort of plug and chug. Sort of. So B is going to be the integral of this. So mu naught I over 4 pi integral of the L cross R. So that's I hat dx cross x I hat plus L over 2 j hat over R cubed x squared plus L over 4, L squared over 4 to the 3/2. Questions at this point? All right. I cross I. Probably doesn't help that I've got x and a cross there, so I am, and I know I just asked the question and then cut anyone off who was about to ask a question. I'm going to make the cross product symbol in black here. And it's already in black there. All right. To differentiate between x along the x-axis and the x of a cross. All right. Questions to here? All right. I cross I.
0.
I cross j.
Okay.
So what I'm left with here is mu naught I over 4 pi integral of, well, I got a k hat there from I cross j, and then I'm left with L over 2 dx over x squared plus L squared over 4 to the 3/2. I now have it in terms of a single variable, so I can put my limits of integration in here. My x is going to go from negative L over 2 to L over 2. I've got a couple more constants I can pop right out, so let's go ahead and pull those out. Ah, yes, back again. Here we go. So I have my magnetic field is equal to U naught times the current over 4 pi in the k hat direction. Integral from bring the L over 2 out, so this becomes L on top and 8 on the bottom there. From negative L over 2 to L over 2 dx over x squared plus L over L squared over 4 to the 3 halves. And how do you do that integral? The physics way.
Work it out.
Yep. And it seems like it's gonna be on something here. And so that will be L U naught I over 8 pi k hat. We're doing the integral. So we get x on top, L over 2 square root L squared over 4 plus x squared from negative L over 2 to L over 2. If we were doing it the math way, how would you solve that integral?
Probably trig functions.
Yeah. Indeed, it would indeed be trig substitution, but we're more sophisticated than that. The math people have done the grunt work for us, so we don't have to. Then plug and chug. So we got L U sub naught I over 8 pi k hat times, I plug in L over 2, and so I get L over 2 L over 2 square root of what'll end up being L squared over 2, under the radical there. And then plug in the negative, minus negative L over 2 over the same denominator. So L U naught I'll stick the k out up front, 8 pi, we get L over 2 times L over square root of 2. And my L's cancel out. Is that right?
Yeah, in the solution, there's no L's.
Okay. My gut was the L should still be there, but I guess not. So that L cancel out with that L and that L. That half will cancel out with, or that 2 will cancel out with the 2 there. And so I end up with U naught I square root 2 over 4 pi. That's for one side of k hat. And then multiply times 4 to get the full solution. So unless there's careless error, U naught I radical 2 over pi k hat. Does that match what they got? No?
Yeah.
Okay.
To be fair, they did it in like 3 steps, so I couldn't really follow anything, so I can't really see.
All right, so that was 24. Oh, they just started with the formula.
Curious what that formula is, because I think they use it again on 79.
So they're using equation 30.8. The bent wire. Nope. There's 30.10, 30.9, 30.7. Slowly narrowing this down. There we go. 30.8. Where they take a finite length of wire of length L and finding the magnetic field at distance R away. And that, what I did right here is just doing it the long way. So they ended up with a, oh. They did end up with an L. All right. I'm still confident with the process. Obviously left something off at some point, so ITL across R over R cubed, good with that. R is a vector, let's L over to J hat. Did I read the problem correctly? That's 24. Wires bent in the form of a square loop, the sides length L, steady current I flows in the loop. So those are length L, it's smack dab in the center, so the distance would be L over 2 there. I'm good with that. DL is a vector in the direction of the current flow. So that would be I dx cross my R vector, which is X I hat, plus L over 2 J hat, and then X squared plus L squared over, so that would be L over 2 squared, which is L squared over 4, 2 3/2, good with that. So I cross J is K, so what's with L over 2 dx, fine with that, that L over 2 comes out. We have 4. X squared plus L squared over 4 to 3/2. I K hat, and then we did the integral. Let's make sure I plugged and shoved into that one correctly. So dx over x squared plus square root of x squared, oh, 3/2, that, yeah, I was on the right one there. Oh. That should be squared. That was the problem. So squared. So that would be L squared over 4. So L squared over 4. One of those L's gets canceled out. So we're left with an L there. That would, 4 goes to negative 2 times. So this becomes 2, I've got an L on the bottom. Then when I multiply by 4, I get 2 mu naught I radical 2 over pi k hat, which I believe matches their answer, although they left the answer, unless it continues on the next page, which it does not. They had their answer as 2 radical 2 mu naught I over pi r. R is the distance from the line in question to where the point in question is. So basically it's from the middle of the side to the center, which is L over 2. So that becomes L over 2. So you multiply by 2, well, multiply by the reciprocal, and you get 4 radical 2 mu naught I over pi L. Oh. L. factor of, oh, my gosh. If you multiply this by 4, you get a 4 there. Oh, wait, I see where I got the 2 from. So multiply a factor of 2 somewhere. I know there's careless error somewhere down. Hopefully you've got the gist of the process to take, despite the careless error.
So that'd be, I also was a little confused on 21. I think they use the same formula, so.
It sure looks like it. So 21, they had counterclockwise current of 7 amperes flows in a square metal loop with the sides. What's the magnitude of the magnetic field at the center of the loop? So 24 is basically the generic version of 21. Yeah, it should be the exact same problem. The only difference is 21 has numbers and 24 has letters.
Where'd they get that formula from?
They derived the formula earlier in the chapter.
It looks like 79 uses the same formula again, except with more than 4 sides.
Yeah, on page 944, well, starting on page 943 and into 944, they derived the formula. I think it takes some of the fun out by removing the necessity for you to do calculus, which is always fun. I assume that's the feeling you have when you take calculus, is this nonstop. It's a nonstop thrill, right? It's joy. You get warm fuzzies. Do I give that formula to you at all? So that would be chapter 30, I would give it to you, huh? I don't think it's one of the formulas I give you.